friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I show design analysis and optimization of a pressure vessel using SolidWorks. So for analysis, we have to start with a simple model. Let's start that model using the front plane, normal to. We'll start with the central line. Next, we can start with the normal line. On the top side, we can provide a specific arc. Similarly, we can do the same thing on the bottom side also. We'll start with arc. Complete. Now, next to that, we can provide smart dimension to this one. And this one will be having radius 157.2 millimeter. And this one also will be same thing. And the height of this one will give 400 millimeter. Done. Next to that, we can provide offset distance at the outer surface of this drawing. So offset entities, select that object. It is done, and the offset distance equal to 10 millimeter. Again check. Next one, we have to close this drawing using straight lines. Top part is done. To do the same thing on the bottom part also. So the drawing is complete. Exit from the sketch. Now select the sketch again and features revolved wash base. It will revolve with respect to the central line. It is revolved already, so we got the pressure vessel already, right? This is our pressure vessel, so green check. Now we can hide this sketch. This is our drawing. The sketch is hidden, right? Okay. Next one, we can provide material to this one. As let's take material, it will be steel definitely. So we're providing material, this one as steel metal, and it will be steel definitely. Let's consider polysteel. And for better appearance, we can change the appearance like little bit of white with ambient occlusion. This is our model. Now we can do one thing, we can color this part also. As it is a pressure vessel, let's say this one as like a LPG cylinder. So we can provide color to this one as red. So this is our pressure vessel, right? We have to go for analysis. Okay, done. Now we can save this part by the name of pressure vessel. Saved. Now we can go for analysis. We're starting this analysis from simulation, and we have to start with new study. And it is a static structural analysis. We can rename this one as pressure vessel, right? Green check. This is our study. First of all, we have to provide material to our object. So apply edit material, and we'll take STM A36 steel, which is having elastic modulus equal to 2E5, 2 into 10 to the 5 Newton per millimeter square. So apply and close. Material is provided. Next one is very important thing, we have to provide fixture, right? So while providing fixture, we have to see that the model should be free. When the pressure is applied inside, it will be having a tendency to be bulged. It will be like a balloon which will be trying to explode from inside. So from outside, the fixture should be provided in such a way that it should not suffer any kind of constraint along the path of its propagation. That means its deformation already changes. So as we are applying pressure from inside, it will be deformed, stresses will be generated inside. So by the application of stresses, it will be deformed definitely, and it should not be obstructed from outside in such a way that deformation is getting obstructed. It should not have any kind of obstruction against its deformation, right? So in this way we have to apply our constraints, these fixtures. First of all, we have to select the fixture, and we have different types of fixtures, so better we start with advanced fixture. Now we have a lot of different options. We can select any one, but in this case it will be better to start with the option of cylindrical faces, right? We'll select that one. As this is cylindrical faces, we'll try to restrict the rotation of the cylindrical faces, right? So select that cylindrical faces. We have selected the object. Now we have to restrain the rotation of these cylindrical faces, right? So what we'll do is, this is circumferential rotation. That one we have to provide 0 degree rotation. That means it is constrained to rotate. It will not rotate at all along this circumference. It will not rotate. Its rotation is restricted. Okay, done. Now another constraint is required. We'll try to restrict the motion of this one along this axis, right? Axial movement of this pressure vessel we'll try to restrict. So again, fixture, we have to apply advanced fixture, and here in this case we'll apply something different. Let's select the reference geometry. So we'll select this plane, and with respect to some reference geometry, this plane will be constrained to move in the upward direction. So with respect to some reference, let's select the axis of this one as the reference. So we can select that axis, and its motion or is restricted along the upward direction. That is, its axial movement is restricted. Okay, done. Next one, you have to apply load or pressure inside this one, right? So it is better to select the segmented view of this model for application of external load. We'll cut this model along the front plane. Now we have to apply the external load. It will be pressure, and we are applying 10 megapascal pressure. So we are applying pressure inside on 3 different surfaces. Pressure is applied. Next part, we have to go for mesh. We can do mesh and run together, but in that case we will not have control over this mesh, because we know that in case of finite element analysis, better the mesh, better is the results. That means if you want to go for convergence criteria, we have to go for meshing again and again, and at certain time, when with change of mesh there will not be any variation in results, we can say that our result is converged. Okay, right? So we have to start with mesh, create mesh, and as we know that more the numbers of nodes or elements, the better will be the results. So we can go for finer mesh. In this way, numbers of elements will be more, numbers of nodes will be also more, so we'll have better results. We'll check. Meshing is going on. It is done, right? We have got our mesh. Now we have to run this simulation. Run this study. So we got our results. It is showing that yield strength equal to 215 megapascal and 1 meter stress equal to 151. It is safe, right? But actually, in case of pressure vessels, we are not considering 1 meter stress. 1 meter criteria is depending on distortion energy principles. It is based on yield criteria. Now in this case, we have to find out this hoop stress and longitudinal stress. We'll find out this later on. First of all, we can change this unit from pascal to megapascal. We have to go for edit definition and we'll change the unit from Newton per meter square to Newton per millimeter square, that is megapascal. And also the scale will change to true scale. It is actually deformed one which high deformation is showing. With true scale you can see it will be little bit changed. You can see the drawing again. With true scale the value is also same but the deformation is changed a little bit. Okay, this is our first result for one measure stress. Now the thing is, excluding one measure stress we can see also displacement and strain also, but we are not bothered about these things. We're mainly bothered about to find out the hoof stresses in this case. Like, okay, this is our displacement and this is our strain. Okay, done. But we are bothered about to find out these hoof stresses. So what we'll do is, again, edit definition, and instead of strain we can change it to this strain, right? We have to change it to first stress value. Will change it. There is one measure stress. From one measure stress we have to change it to hoof stress. So edit definition and one measure stress is available here. We have to change it. Now here in this case you can see hoof stress is not available, right? So here in this case you can see that first principal stress is equivalent to hoof stress. The maximum stress developed inside this pressure vessels, it will be hoof stress. So it will be, in this case it will be first principal stress. So let's see that one. It is showing that it is 164 megapascal, right? And the yield stress is 250, so definitely it is safe, but the factor of safety is very less. It is 1 point something. We have to increase that factor of safety. Designing of pressure vessels, actually we have to be very much cautious about the factor of safety. So we have to increase this factor of safety. That one we can be done using optimization, right? Okay. Now we have to find out the longitudinal stress. So edit definition, we can change it from first principal stress to second principal stress, that is longitudinal stress. It is equal to 102 megapascal, right? Okay. Now some other things we can see that this stress distribution you can see in the form of vectors also. Okay, so we'll do it again. Edit definition. From advanced options we can see that stress in the form of vectors, vector plot. Okay, so this is vector plot. Now we can change this pattern of these vectors also. Let's change it. From vector plot options we can increase the thickness and the density also. This will be density, we can increase the density, so numbers of vectors will be increased, and the size of this one also can be increased. Right, this is the stress, longitudinal stress. You can see the distribution. Now it will be better to see in the form of an animation. We'll animate this one. Let's animate it. It's very fast, we can make it slow also. This is the stress distribution, longitudinal stress. Okay. Next one we'll see the stress distribution in hoof stress. So again, edit definition, we'll go back to first principal stress, and from advanced option it will be show as a vector plot. Okay, check. So this is actually our hoof stress, which one will be trying to divide the pressure vessel into two equal halves, right? This hoop stress is the pressure inside the vessel which will try to make the cylinder into two equal halves. This is the hoop stress, right? You can animate this again. Okay, done. Now from this data we can find that our hoop stress is 164 megapascal and our longitudinal stress is 102 megapascal and yield stress is 250 megapascal. It is safe, but the factor of safety is very less, right? Now we can do the same kind of analysis in a different approach. What we'll do is let's go back to the previous model again. You can go for a different analysis. So new study, you can see the complete view of this model. This is the completed model. Now very important thing I told at the beginning, that to have converged result we have to go for mesh again and again. That is, discretization is very important in finite element analysis. So better the mesh, better is the results. Now sometimes it may so happen that if the size of the model is very big, we cannot go for further meshing. That means the software has got some limitations. So to avoid this type of things, what can be done is, if the model is symmetric, we can break the model into simplest forms and go for analysis using symmetric boundary conditions. That one we will follow here because this model is symmetric definitely. So we will try to divide the object into different pieces, and for each cases we'll try to find out that stresses and see the results with the previous cases. Okay, first of all we'll divide the object into two equal halves and we'll go for analysis. Okay, so start with here, insert, cut with surface. You can cut this model with respect to front plane. So it is cut. You can see it is a half model of this one. If the model is half, so we can go for more finer meshes. More numbers of nodes can be generated. In that way, we can have better results, right? So as we have started a new analysis by the name of static 2 default analysis, we have to provide material to this one. So it is a new study by the name of static 3 default, and we have to provide material for this one. Let's apply edit material, and we are planning to provide the same material what we applied before, that is ASTM A36 steel, which is having modulus of elasticity 2E5. So apply and close. Material is applied with this model. Next one we have to apply boundary conditions, that means fixture to be applied. So fixture, and we have to apply the advanced fixture. As I told that this is a symmetric model, so we have to apply symmetric boundary condition that will restrict the motion of this cylinder across this circumference, right? So we'll apply symmetric boundary condition. To select the surface, done, grain check, one boundary condition is applied. Now another thing we have to do, that means this one should not have any kind of motion in the upward direction, that is axial movement of this one should be restricted. So we can go for another boundary condition, fixture, so it will be advanced fixture. So we are using reference geometry, right? Let's select this plane, and with respect to this one, this plane should be having restricted motion in the upward direction. So we have to select another reference object. We are selecting the axis of this one. Okay, so select the axis. So with respect to this axis, this plane will be having restriction to move upward direction. That means this plane cannot move in the upward direction, right? This plane, so it can move, the other part, the top part can move, right? But this one cannot move. This one is restricted to move in the axial direction along the axis. So you can check. the boundary conditions have been applied. We can make it hidden. Now we have to apply the external load or pressure. External load, we are applying pressure. We have to apply the load of 10 megapascal, so it will be Newton per millimeter square, and the load will be 10. Select that location. Green check. We have applied the pressure inside this one. Okay. Next one, we have to go for meshing. Directly you can go for mesh and run, but to have better control over this body, we have to create mesh with finer mesh. So go for finer quality mesh. Green check. Meshing is going on. It is done perfectly. Now we have to run this simulation. Let's run this study. So we got our results. It is showing 1 meter stress equal to 152 megapascal and yield strength equal to 250 megapascal. I can change the unit like before, edit definition, and change the unit from pascal to megapascal. And instead of 1 meter stress, you want to see first principal stress, which is equivalent to our hope stress. We'll see that hope stress, it is 163 megapascal. What we got before, it is exactly same. Now again we will check our longitudinal stress. So edit definition, instead of first principal stress, we'll change it to second principal stress. Green check. You can see like before, it is 102 megapascal, right? So with segmented model also we can see the same results, right? Okay, again third time we will go for another analysis, new study by the name of static default 4. What we'll do is we have to divide this model into 1/4 of the complete model. So we'll start with cutting the face. So insert cut with surface, and we want to cut this model with respect to our right plane. So we have cut this one. Now it is 1/4 of the complete model. As the model size is decreasing, we can do one thing. We can go for better mesh, and the numbers of nodes or element will be increased. So, and also at the same time, the time for this analysis will be reduced. We can have very short time for getting these results, right? It is very simplified result. Actually, these symmetric boundary conditions are applied to have a controlled meshing conditions. So first of all, we have to apply the material again like before. Apply edit material. Like before, we have to apply STM A36 steel. Apply, close. So steel has already been provided. Next one, we have to apply the boundary condition, that is fixture to be applied. So fixture, and from advanced fixture we have to apply symmetric boundary conditions. We have to select that edges on the cut surface. Done. Symmetric boundary conditions applied. Next to that, we have to apply another constraint. That means along the axis, this one should be having no movement, right? Its movement along this axis should be restricted. So fixture, advanced fixture, you can select the reference geometry and can select this edge with respect to some reference. You have to select, let the reference be our axis. So we can see this is having some constraint along upward direction, right? Only this part, but this upper part is free, it can move. Okay, green check. So we have applied our boundary conditions. Now we can go for our loading. That means we have to apply the external load. So external load we are applying, it will be pressure. And see one thing, like if you are cutting the model into half or 1/4, in all cases we are applying the same pressure. Before also we applied 10 megapascal, here also we have to apply 10 megapascal itself, right? So in changing the unit from pascal to megapascal, and the load will be 10 megapascal. Let's select that model, green check. So pressure is applied. Next one we have to go for meshing. So create mesh, and we will go for finer mesh to create more numbers of nodes and elements. Meshing is going on. Yeah, perfect meshing is done, you can see. So finer mesh, we can see. Next one, to run this simulation or run this study, you can see our results. Like before, exactly same result we are getting, like yield strength is 250 megapascal and the bond resist stress is 151 megapascal. As I told earlier, in these pressure vessels, our bond resist trajectory is not applicable. For these pressure vessels, we have to see hoop stress and longitudinal stress. So we'll change it again. Edit definition. First of all, we'll change the unit from pascal to megapascal, and one major stress will change it to first principal stress, that is equivalent to our hoop stress, the maximum stress developed inside this cylindrical pressure vessel. Okay, we'll check. So you can see here again the same thing like the before, it is 164 megapascal, that is the first principal stress or hoop stress developed inside this cylindrical pressure vessel. Next, when you see the longitudinal stress also, edit definition. Instead of first principal stress, we have to see second principal stress. Green check. Again, it is showing it is 101 megapascal. So in all cases, whether it is segmented one or it is complete model, in all cases we got similar results. And in case of segmented model, we have a lot of advantages. That means we can have better meshes or finer meshes, and in this way we can have more numbers of nodes and more numbers of elements, can have more data, right? In all these three different types of analysis, we got the same results. You can see that hoop stress is equal to 164 and our yield stress is 250. That is, factor of safety is equal to yield stress by your working stress, right? So factor of safety is not very high, it is near about 1 point something. What we'll do is we'll try to decrease the hoop stress in this case. Hoop stress 164. So in optimization, what we'll do is we'll try to reduce this stress value, and for reduction of the stress we have to increase the thickness of this material, right? We are planning to have a stress of 125 megapascal, right? That means we want to have a factor of safety near about 2, because in this case we have modulus of elasticity or yield strength equal to 250 megapascal and factor of safety equal to yield stress by working stress. So this is our goal. So for having 125 megapascal hoop stress, we have to change the thickness of this model. At what thickness of this model the hoop stress should be equal to 125 megapascal. That is our goal. So we'll start with a new design study, and for design study we have to get some input variables which are responsible for changing these stress values. The values may be in the form of dimensions, maybe the thickness, maybe the length, maybe the radius, etc., all these things, but we'll consider the thickness of this material, of this model, as the main variable for this changing stress. So we have to select the thickness of this model. We can select this from here, add parameter. Now all the parameters, you can see which one is more predominant for changing stress values, that to be selected. You can select all other parameters also. You can optimize these things. If you optimize these things, it may so happen the length may be changed, radius may be changed. So we are not planning that one. We are planning to have the length to be fixed, only the thickness to be changed. So for that one, we have to select the thickness as the input variable, right? Let's select 10 millimeter as the input variable. which is responsible for changing the stress values. We have selected 10 millimeter and that to be defined as thickness. So okay, we're considering only thickness as the input variable, which will change the stress values, right? And we have to select some specific range. Initially, the thickness of this model was 10 millimeter. We are planning to have the thickness from 5 millimeter to maybe in the range of 25 millimeter. Let's select that range from 5 millimeter to 20 millimeter. And step, that means by how much it will increase. Let's select the step as 1 millimeter only. That means this thickness will vary by 1 millimeter. Next one, we have to select some constraint. Add sensor. That means stress value we have to define. So mass properties we have to change it to our simulation data, and here the stress value we have to define. Let's select that first principal stress, and the unit should be megapascal. Green check, and we have to define that first principal stress should be less than or equal to, we can define this one as less than 125 megapascal. It's less than 125 megapascal. Initially it was 164. Now what we want to decrease the stress developed inside, and for that one we have to increase the thickness of this model, right? Done. Stress value decided as it should be less than 125 megapascal. Next one, we have to select the final goal. That means definitely we have to decrease the mass. We have to minimize the mass. So again, add sensor and mass minimization. So we have to select that mass. Its current mass is equal to 1845.9 gram. That means 1.85 kg approximately. Approximately equal to 2 kgs. So what we have to do is we have to optimize this mass. So green check. You can see that we have got near about 16 numbers of scenarios. That means 16 numbers of iterations will be going on, and with this specified range of 5 millimeter to 20 millimeter, we are planning to have the stress value below this range of 125 megapascal. Sometimes it may so happen that within this range we may not get our desired output. In that case, we have to change the value again, right? So let's run it. So iterations are going on. As the iterations are going on, we can see the dimensions of this model is also changing one by one. At 10 millimeter thickness, the stress was 164.55 megapascal. Now it will calculate at 5 millimeter. Definitely it will be stress will be more at lower thickness. You can see here at 5 millimeter thickness the stress value is 324.5 megapascal, and in this case the weight is also less. Weight is 902 gram. Next one, it will be 6 millimeter. Definitely it will be less than 324 megapascal. Let's see how much it is coming. At 6 millimeter it is 270 megapascal. Like this way, as the thickness is increasing, the stress value also will get reduced. By the same time, mass of that one also will be increased. Okay, so in this way we have to find out at which thickness mass will be less, by the same time stress will be less than 125 megapascal. Okay, it is whenever the iterations are finished, we'll see the results and analyze it. Okay, now we got our results, right? You can see all the results one by one. We'll check. Like first and second, we told already. Initially the thickness was 10 millimeter, and on that thickness we got our stress to be 164.55 megapascal, and weight of that one was approximately 1.8 kg, right? So as the thickness of this material is increasing, the stress value is also decreasing. By the same time, mass is also increasing. Now our optimum result is at the thickness of 14 millimeter, we got the stress value 119.11 megapascal and the mass is 2.6 kg. We got a lot of results, like you can see at more than 14 we got all cases stress value is very less, right? You can see when the thickness is 25 millimeter, the stress value is 69, but mass is very high. Similarly, at scenario number 18, when the thickness is 22 millimeter, our stress is 77.96 megapascal and the mass is also 4.283 kg. So with all this data, we got our optimum result as at 14 millimeter thickness, stress, that is hoop stress, is 119 megapascal and the mass is 2.63 kg. So this is our optimized result. So from this study, we learned design analysis of a pressure vessel, and we did the analysis using the complete model, by the same time segmented model also by using the half model and the quarter model of this pressure vessel. In all cases, we got similar values of hoop stress. In this analysis, we found that inside this model, we applied a pressure of 10 megapascal and hoop stress induced inside this model was 164 megapascal. And the material was having yield strength equal to 250 megapascal. So we can say that factor of safety is not very high, it is less than 2. It was 1 point something. So in our optimization, we planned to increase the factor of safety by the amount of 2. So what we did, we planned to minimize the value of our hoop stress to be 125, and to get this minimum stress of 125, we have to change the input variable. The input variable was, in our case, thickness. And with optimized result, we got that at a thickness of 14 millimeter, our stress, that is hoop stress, developed inside this model was 119 megapascal, and with this condition the mass of this model was 2.63 kg. Okay, so this is all about our today's analysis and optimization. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.